Hi guys, welcome to this video. This video is the second video I'm doing about turboprops, the first one being about fixed shaft turboprops, of which a representation is here on the top left. Now, what I would suggest is that a lot of the stuff I'm going to talk about I've already mentioned in the first video, so if you're not familiar with that, it might be worth going back and having a look at that, just to become familiar with things like the PCU, the propeller control unit, and the whole ethos behind this. However, this is our fixed shaft turbine, and we'll just do a very quick run through of it. Make sure we've got the right bits and bobs. Okay, so if you remember rightly, all engines pretty much work on 4 elements, because I said 4 there, work on 4 elements. They use suck, squeeze, bang, blow. Now, the suck is obviously about here where the intake is, and it comes in. The compression stage of the turbine is here, which is 2. The bang is in there, and the blow is this final bit at the end. Now basically what happens, as a very brief recap, at the suck, air is drawn in at the front of the engine and sucked in through the air intake. Squeeze, the compressors, basically the first set of blades that the air meets is a compressor, and that forces the air into the combustion chamber, or draws the air into the combustion chamber. This third area here is where you have your bang, which is in the combustion chambers, at which point you inject the fuel into the air to create an air-fuel mixture. It all goes bang, and as a result of that you have hot gas and air which is forced out the back of the engine, and as it passes through in our turboprop, basically what it does is it turns this bit here. And this bit here is the power turbine section. It's important here, so that's the power turbine. Okay, and this first bit at the front is the compressor. Okay, and obviously all of that is bolted to the prop hub, upon which is bolted the prop. Now the only thing that's missing on this picture here is there's also a bit here which is the FCU, or the fuel control unit. Now when we went through it first time, this is just a very brief 5-minute recap. We had our 2 sets of controls. Let's draw that grey, because quite often in the cockpit you'll find this is grey. You had your condition mixture, your condition lever, and you had your power lever. If I say throttle at any point, then I do apologise. Now the power lever is connected to the fuel control unit, and the condition lever is connected to 2 things. The first thing it's connected to is the prop control unit. The second thing it's connected to is I suppose the best way of describing it is a fuel on-off switch, also known as a fuel cock. So basically what then happens is, if we're operating our engine, let's assume that it is all up and running. What does the condition lever control? The condition lever controls the propeller control unit, and that sets the RPM. Now you've got to remember that all of this is on one shaft, so as a result of that there is a direct ratio. There's generally here you will have some sort of reduction gearbox, because obviously if this is spinning at 25,000 RPM, your prop can't work at 25,000 RPM. You're looking much more down towards I don't know, 2.5 to 4,000 RPM, something like that for a prop. But obviously what you can consider it all to be one piece of equipment, for want of a better way of putting it, one complete system. But anyway, your PCU sets the RPM of the blades, and it maintains the RPM. And then you've got your fuel on-off is largely insignificant from our perspective. We're looking at running engines. And then the power lever, what does the power lever? It controls amount of fuel going into the engine. Okay, so if we want to increase power or thrust, here's the brief way in which it works. One, you advance power lever. As a result of that, more fuel goes into the engine. As a result of that, you have a bigger bang. Then you get more gas forced through the power turbine blades, which are these ones here. So you've got more gas being forced through. As a result of that, the turbine has a greater, or it has an increased force trying to turn it. However, the PCU tries to keep the RPM constant. The only way it can do that is to increase drag. So the air is stopping this thing from rotating faster, and the way it increases the drag is to increase the pitch on the blades, which results in increased thrust. Okay, so there you go. Fixed shaft turbine in a nutshell. So we're going to do something very naughty with this at this point. What we're going to do is we're going to convert it to a free power turbine. We're going to get our hacksaw out and we're going to just chop it through here. We're going to absolutely maim it. We're going to get our best B&Q hacksaw out and we're going to take it to the engine and we're going to split it into two parts. And the front part we're going to consider to be one system, the back part we're going to consider to be another system. So if you just bear with me, I'll clear all this down and we will start with our free power turbine. Okay, so let's have a think of layouts. What we've got now is we've got two systems that we need to work together. So the first half, in effect, is going to be the gas generator. And the second half is going to be the free power turbine. One day I will learn to write. So you've got two parts to it. Now there is going to be a two real different layouts. So the first one is what I'm going to term as a straight through. And the other one is going to be what I will refer to as a reverse mounted. Now, examples of each. The best example of the straight through really is either the CT7, which is mounted on the Saab 340, for example. The other one is the Pratt & Whitney 150, which is mounted on the Dash 8. Q400, and in this case this is what we're going to use for our example because I've got the Majestic Dash 8 which does a very nice job of it. Just as an aside, the reason the Majestic Dash 8 is very good at it is because it does an awful lot of modelling outside of FSX and P3D. In effect, what they've recognised is the fact that turboprop modelling in those two programs is really quite appalling. So they've basically programmed all of the modelling outside of the actual sim, and in effect what they then do is inject the results back into the sim to tell the sim what it should be doing. The best known example of a reverse mounted is the PT6, which is quite often used in things like the Cessna Caravan, Twin Otter, and the example we're going to use is the Beech 1900, and in this case it's going to be the D model, and we're going to use the Carenado version of that. This sort of setup and layout, obviously being being the Beech. It's also got the King Air series, for example. There's all sorts. This is a very, very common engine. I'm not sure, but I think if my memory serves me correct, it's the most common turboprop engine which is in the world at the moment. I think it might be that the Rolls-Royce Dart is the most popular one ever, the most used one ever. I seem to remember that from the depths of my memory. But at the moment, the most exclusively used one is the PT6. However, we have two setups here. So we've got our suck, squeeze, bang, blow as we had before, with the suck, the squeeze, the bang, and then the blow. However, that's how a normal jet engine would work, a normal jet turbine engine, for example. However, in terms of the energy of this air, previously what we did was we bolted a shaft to the front, and as a fixed shaft we then decided we're going to use that to drive our propeller. And there's a reason why I've done it in different colours, which will become immediately apparent. But we don't want to do that now. We've said we want to fix. Look at that. Look at the lighting and the effects, and oh, that's beautiful. I ought to sell that. There's a reason we don't want to do that. We'll go through that in a minute. But instead of having this and all of this bolted together, so you've got your compressor, your shaft, and your power turbine section at the back, what we're going to have is just a self-contained turbine. And instead, what we're going to do now is we're going to take this and put it on a separate shaft. And that separate shaft's going to go all the way through the middle of this bit. And then we're going to have new turbine on the back of that. No, I don't want to do that. Don't want to do that. Let's do this. Let's just extend those out so it's quite apparent that that's within the casing. Okay. So now what we've got is a situation where this air that's being drawn through exploded in our combustion chamber and then fired out the back. This bangy bit here, the air is now being forced out at high pressure. Now if it were a normal jet engine, you would have said at this point that that's just going to be pure thrust. However, it's not going to be pure thrust here because we've put a fan blade in the middle of it. And we've been really quite awkward with putting our fan blade in because it's right in the way of where that air's trying to go. So what will the air do? The air will turn this blade. So consequently what we have is we have our air going in, being drawn in, squeezed by the compressor, into the combustion chambers where it goes bang, fired out the back, and as it goes out the back it passes through this extra turbine that is not connected. Here's the key thing. These two things, this bit here and this bit here, are not connected. So they can turn independently. So herein comes the big question then. And this is the probably the biggest question that could be asked out of this. Why? If we've already got a fixed shaft turboprop that works fine, why on earth would we want to start making it more complex by breaking bits up into different sections? So, because what we've got at the minute is we've got this section here, and we're going to introduce a new term here. This section here, which is the black shaft and blades, is called the gas generator. And it does exactly what it says on the tin. The whole purpose of the black section, these blades here, this blade here, the compressor at the front, the shaft, and then the turbine at the back, the whole purpose of that is just to generate a gas flow. And then your second bit, the purple bit, is your free power turbine with its shaft, which is then attached to the prop hub and therefore the prop. Normally you'll have some sort of reduction gearbox as well. So, yeah, why? Why would we want to make a simple system more complex? Well, there's a number of reasons. The first one, efficiency. You see, the problem we had with our first engine is that we were expecting the turbine section and the prop section to work hand in hand. And the issue is there that what's efficient for the prop may not be the same as efficient for the main turbine engine. So what we've got now is we've got two systems, which are the free power system and the gas generator system. And it might well be that the whole point here is that the two systems can work at different speeds. And as the performance of the engine changes, as the demands made of the engine changes, then ultimately each one can settle into its most efficient configuration. Each one can settle into its most efficient speeds. They're not tied together. So, are there any other advantages to it? Well, yes, there are. If you remember when we spoke about about fixed shaft turbines, one of the problems was that in fixed shaft there were problems if the prop drives the engine. So they were always producing approximately 30% thrust, so that the engine always drove the prop. This is now less of an issue because the two are not connected. There's no physical link between the two. The two are obviously related. So, you know, if this section is driving at full chat, you've got to have some sort of effect on the prop system. But fundamentally, we haven't got the same issue that if the prop is independent from the main gas generator, you haven't got a physical link. So this is less of an issue. We can get rid of that largely. Next one, APU. Okay. There's a lot of smaller turboprop aircraft, and I'm thinking particularly of things like the Twin Otter. Something like the Twin Otter does not have an APU, but it might be nice in certain circumstances to basically still have your ancillary services running. And how would you do that? Well, let's face it, if you've got an engine, which is your gas generator, you can attach services to it. And because it's not fixed to the prop, certainly at low RPM, this can run and the prop can be held stationary. So now you've got the ability to have a pseudo APU. Now this is very common in helicopters. If you've got a large turboprop, then quite often what you end up with is a separate APU anyway. But in the smaller turboprops, things like the Twin Otter, you have the ability to separate almost the two systems completely and to leave one stationary whilst the other one is running. And therefore what you get is a pseudo APU, is probably the best way of describing it. So those are three really big advantages. However, the world is not all rosy, is it? There has to be some form of disadvantage. Actually, while I think about it, there is another form of advantage that I can think of, and that is engine changes and maintenance. Right. I'll go through it in a moment, but there is a layout which is common to the PT6, and it's a bit odd to get your head round. Let's say our aircraft flies in that direction. So we've got our prop as normal at the front of the aircraft. We've got the tail section over here. You've got your wings, and so on and so forth. And the prop's attached to a free power turbine. So that's what we would normally expect. However, what they've done is they've reversed the engine. So let's draw it like this. Here's our gas generator. Now you can see obviously what it wants to do now is it wants to draw the gas and the air through this direction. So it's backwards and then it comes out. Now that seems a bit odd, but in effect it's very easy to get around, because what you can do is you can have your air intake come around like this, and then as a result of that you can then have your exhaust passes through the free power turbine and then goes that way. So basically what you've done is you've got a reverse installation of the engine like that. So hopefully clear as mud. We'll go through that in a bit. But one of the things there is now you've got a situation where the shaft doesn't run through the middle. So if you want to do an engine change, I remember from when I was in the Sea Kings, it would be called an ECU or an engine change unit, or you could do maintenance on the prop and the free power turbine. But these two were not just separate systems. This has got two separate systems, but they're, if you like, co-located. This now not only has two separate systems, but it also has two separate systems that in effect can easily and readily be unbolted. So that's one of the other sorts of advantages. If you imagine if you've got a fixed shaft, it's all bolted onto one shaft. Another advantage of this one, by the way, is you have a very short shaft between the power turbine and the prop. So this bit here, look, is very short. If you compare it to what's up here, this very long turbine blade that goes all the way up here, look, compare that to this bit here. And it's quite obvious that this is going to be mechanically stronger because it's much shorter. Now, of course, the advantage there is potentially weight. If you imagine this is a very long piece of metal, here what we've got is a very short piece of metal, and it doesn't take a genius to figure out that short bits of metal weigh less than long bits of metal. And in addition, if you like, the maintenance saves time and money with this sort of layout. So the PT6 is a common layout for that sort of thing. But anyway, we diverge from what we were saying. However, everything in life has advantages and disadvantages. What could be a disadvantage of this? And this is the key single disadvantage that can be encountered in these circumstances. Lag. Now, lag is a pilot's enemy and can be considered as a delay. So it's the delay between the input and the effect. Now, one of the big things with a fixed shaft is that everything is one system. So you had fixed shaft, had a minimal, it still does have some, and one of the key areas where it still has that delay is in the prop hub with the constant speed unit. However, what we've now done is we've introduced it. In effect, we've got three interfaces. So let's write it up here. We've got two interfaces. One is between the gas generator with its inertia and the effect of injecting fuel into it and the power turbine. Because these things have inertia. So the gas generator, when you dump the fuel in, it will obviously accelerate. It will generate a bigger bang and more air gets drawn through and it will accelerate. Obviously that air then has to take effect on the power turbine, and there will be a delay as the power turbine tries to catch up with the change in the airflow that's coming through generated by the gas generator. And the second, so that's the first interface. The second one is between the power turbine and the actual prop, and that's through the prop control unit or governor. Now I haven't mentioned the PCU because in effect it's the same as previously. However, we'll draw it in for completeness. Where's my thing gone? I suggest if you want to know more about the PCU, the easiest thing to do is just go back and watch the previous video. But there we go, there's our PCU. And its aim is to keep the RPM constant. And then the other piece of equipment that we needed to recall was in relation to the gas generator. And the gas generator basically is controlled by the FCU, the fuel control unit, or the fuel computer, and that controls the fuel flow. And there, in a nutshell, is a free power turbine, complete with why we would have it for the efficiencies and the various things, and the very basics about how it works. Now, as I've alluded to when I was down here, there's a couple of different layouts, but this is the very bare bone basics of its layout, or how it's structured. So what we'll do is we'll just quickly get rid of this, and then we will go into the actual control of the engine and how the thing operates. So I alluded in that to layout. Now, this is what we've been looking at up to this point. So we've got our separate free power turbine and our gas generator, the black bit in the middle. And in effect, this can be considered to be a straight through layout. Now, this one is the kind that's fitted as the PT6. Now, it's renowned as one of the most reliable turbines in the world, but it does have some odd features. And the first odd feature it has is that where you look at this, and you can see the airflow, we're flying, let's do it like this. Direction of flight. So we're flying in this direction. And in effect, you can see this is similar sort of layout to a normal jet engine. We're flying left to right. The air, as a result, flows in the engine from the right and travels straight through. Now, there are different sort of combustion chambers. We're not going to go into the depth of that. But fundamentally, if you like, the airflow is consistent with the direction of travel of the aircraft, i.e. the aircraft travelling from left to right. This is the sort of engine that is in... let me do it in this. In fact, this is the sort of engine that's in the Dash 8 Q400, which we're going to have a look at. It's also in a number of other aircraft, but the critical one for us, it's also used in aircraft such as the CT7, for example. Engines such as the CT7 in the Saabs. But fundamentally, the one we're interested in is this one. And it's, as I say, it's a straight-through configuration. So if that's a straight-through configuration, how else can you do it? Well, let's just put our combustion chambers in here so that we can orientate ourselves. Now, previously what we had is our turbine shaft going straight through the middle. So what we're going to do now is we're going to turn it on its head. And we're going to put, in fact, let's just do it like this. We're going to put the turbine at the front of the aircraft. And at this point, it's very much a case of, well, what the heck is going on here? Why on earth are we doing this? So let's just move that to there. Do ourselves a prop. Most massive prop, because we want to go most fast. Actually, to be fair, there's a speed limit on the basis of the aerodynamics of the prop as to how fast you can go. But for the purposes of this, we want to go most fast. So we're going to have a big engine and a big prop. So there we go. There's our prop. Well, hang on a minute. Now we've got a problem. If the airflow is going this way, then it's going to pass through the free power turbine before it gets to the gas generator. That's wrong. It needs to pass through the gas generator first. So what you'll find is a situation like this. So there's a big hole, and the air actually gets drawn in from the rear of the engine this way. So you've got your cold, fresh air being drawn in from the rear of the engine like that. And it hits the first stage. This is now, if I go back over here, let's choose a random colour that we haven't used much before. Let's go for orange. Right. This section, if you remember, was the compressor. And this section was the turbine. And then obviously we had our free power turbine. So they were the components. Now what we've got is we've reversed the gas generator. So this is now your compressor. And all it is just imagine it turned 180 compressor, ER, 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 OR, 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 ER, UR. So all we've done is just flip this 180 degrees. So now here you've got your turbine, and you've got your free power turbine here. And at this point, what you then have, in fact, let's just get rid of that. That's in a really awful place. Let's draw it. Let's go back to this. What? I don't want that. Undo. Let's choose our horrible green, horrible orange, I should say. So that's your free power turbine. And you'll see it, there's like a bizarre whacking great big exhaust which is visible on PT6s on things like the Cessna Caravan, and it's a huge great thing. You'll see it like this. And actually what's happening is it's taking the hot gas, because if you imagine this cold air has now gone into the combustion chambers. From the combustion chambers it burns, it creates hot exhaust gases at high pressure which come through here, come through the free power turbine. They do lose their energy as they come out, and then obviously it comes out this way. So now our question is, what's it doing? What am I doing? And we figure that out using gauges. Just using the position of the controls isn't really adequate enough for us. It would be a bit hit and miss. And the gauges that we would use initially for the fixed shaft are as follows. The first thing you would want to know is you want to know how much fuel you're dumping in, because that's come directly from the power levers. The second thing you want to know is if you're dumping all this fuel in, you want to know what temperature it's burning at, because that can be a key limiting factor. Otherwise you'll melt the core of your engine. That temperature will then introduce an element of expansion into the air, and there's also, you know, everything goes bang in there. So really what then is going to happen is it's going to try and drive the shaft and turn the shaft, and you will end up with a torque reading as this thing tries to turn desperately. Then what happens is you've got to remember that one of the things you did set is through the prop control unit. So via the PCU you have your RPM set or governed, and really those are the key critical components that you're going to want. You're going to want temperatures and pressures in terms of oils and things like that, but fundamentally the four main gauges, if you want or if you like, for the fixed shaft are the fuel that's going in, the temperature as a result that's burning in there, the torque. So what torque is being applied to the shaft, and then you also want the RPM so that you know how fast it's turning. And really those are the only key gauges for a fixed shaft. However, the next element to look at is our free power turbine. Well, let's have a think about this. We still want to know the fuel going in. Tick. We still want to know the temperature that fuel is burning at. Tick. We will still need to know the torque. Tick, because that's an indication of the power being delivered to the prop. And we will also still want to know the prop RPM. Tick. Now you'll notice I've got a gap here for number 3. It's not because I can't count, although it is a challenge on some days. And you'll notice that I've also specified that it's the prop RPM. And that's because the gas generator is not linked to the shaft of the free power turbine. So therefore what you need to know is you need this additional one, and that is the gas generator RPM. So really, actually, in terms of engine instruments, there's not really that much additional. Now the only thing I will add to this, and we'll draw it in a very basic form. So spools and stages. What do I mean by these things? Right. They're quite frequently mentioned, but I will just quickly go through a very brief discussion of it. Let's say, for example, we have a twin spool engine. What would a twin spool engine be in the element of free power turbines? Well, a twin spool engine would be something like this. So you'd have your blades coming down like this. Let's just move that over there. And coming down like this. That's your first stage in effect, or your first spool. Your second spool would be exactly as you'd expect for a free power turbine. It's going to be this bit that goes off to the prop. So what happens then is, in effect, each separate system, and that's the best way of describing it, is described as either a spool or... Hello? What's going on there then? I didn't want that. Each separate spool or system is probably a better way of describing it, is in effect a separate system. So what we've got here is two systems which in effect can be considered as spools. So your first spool would be that one there, and your second spool would be that one there. However, the Dash 8 Q400 is fairly rare in that it has a 3-spool engine. What do we mean by 3-spool engine? Well, it's exactly that. We have another spool. And the best way to draw this is going to be to do it like this, I think. So as a further sleeve around, we go like that and like that. So if you imagine, we've now got 3 shafts. We will add the casing just to try and make it a little bit clearer. But we've now got 3 shafts all turning in the same casing. Running right down the middle. Running right down the middle, you have your free power turbine. So we're familiar with this. Outside of that, the first stage would be this red one, or the first spool I should say, will be the red one, and the second spool, if you like, is the green one. Not necessarily in that order, it depends on manufacturers and such like. So what you end up with is not that. What you end up with is another spool. I keep saying stage, I mean spool. So now what you've got is 3 systems. And these two, let me just choose a colour, puce orange. These two are both part of the gas generator, because you can see that they're not connected to the shaft for the actual propeller. You still only have the one free power turbine. So if that's spools, or 3 spool in the case of the Dash 8 Q400, what are stages? Stages, what do we mean by stages? Right, let's imagine we have our normal shaft and we have our normal casing. So there's our shaft inside our normal casing. And the shaft, as we've discussed before, has a compressor stage and it has a turbine stage, and obviously it turns and it's all connected together. Now it's not a twin or 3 spool engine. This would be in effect a very, very basic jet, and the air for the purposes of this is coming in from this direction, the direction of the badly drawn arrow. And the exhaust obviously is coming out in this direction, And just the same as before, we've got our combustion chambers. Now, some very clever boffins at one point figured out that actually one of the things we can do to make it more powerful and more efficient is we can add more blades to the same axle. Okay, so more blades to the same shaft. And then they figured out that if we do it in a number of stages, then what we can have here is, for example, this bit is a 3-stage compressor. And at the back, they cunningly decided to do things like add extra blades on this shaft. That is an appalling line. They decided to add an extra stage on here, for example, and then what you end up with is a 2-stage power turbine, or 2-stage turbine, I should say. Okay, so this is the difference between the spools and stages. It's easy to get them mixed up. Spools, in effect, the easiest thing to think of is the number of axles that are running, or the number of shafts, or axles really, and they're sleeved so they can go inside each other, but they are not linked. So a twin spool engine or a 3-spool engine is, each spool is not linked to another spool. A stage is the number of blades. So this one has a 3-stage compressor and a 2-stage turbine, and those blades are linked on the shaft. So there we go. Hopefully that's clear, not confusing at all. And we'll move on to the next bit. We are now being introduced into the cockpit of our aircraft, and it is a marvellous place. So what is the right hand lever? Well, this is the kind of setup you get in something where it's kind of got a combined condition lever on the right. Quite often you get a lot of the modern aircraft, particularly those with FADEC, only have the 2 levers. And the one on the right controls 2 things. It controls, first of all, it controls the RPM of the engine that you've selected, and the second thing, as we've said previously, fuel on, off, which is the fuel cock. Now there's no real metering in terms of, you know, mixture, but what you do get is you get kind of the ability to set a low idle or a fast idle or whatever it may be, but in effect they are simply just fuel settings. They're not really used to control the aircraft per se. The other lever over here is the throttle. And really all that does in the first instance is control the amount of fuel going in. Now if you combine that with the RPM and the propeller control unit and the fuel computer, in effect what you have is the ability to set an RPM using the right hand lever, and then by varying the amount of fuel going in you get a variable amount of thrust as a result of the propeller control unit. However, there's another element to this left-hand lever, and it's a bit of an odd one. Most turboprop engines and aircraft have the ability to go into beta and reverse. What do I mean by that? Well, beta is where the blades fine off and they become flat or almost flat, and reverse is where they literally reverse the pitch of the blades, and instead of thrusting the aircraft forward, they thrust the aircraft backwards. So if these are prop controls, why are they not on that lever? Well, there's an element of this that actually applies common sense. When you're landing or taking off, your hands in effect are going to be on the throttle. So the last thing you want to be doing when you're in an emergency situation or trying to land on a short strip, for example, is messing around juggling between levers. So what they've very generously done is they've allowed the following idea to work. And in effect what happens is this is your normal alpha range. This is where you control your fuel computer, your fuel control unit. Meanwhile, obviously everything else in terms of pitch is controlled by the RPM. So you've got your PCU, which is working independently. So these two things are not really working together. They're working almost as 2 independent systems. However, in here you've got your beta range, and then in here you've got your reverse. Now, you don't want to be juggling around with the throttle, so in effect if you're struggling to land this thing or you have to do an emergency stop on a takeoff, in effect what you want to do is you want to close the throttle fully. Normally there will be some sort of gate here, which you either have to lift the throttle or pull a little button to get into the beta range. The beta range is in effect a flat or very fine pitch of the blades, and it causes drag. So what does the reverse range do? Well, you've got to lift it over another gate. So you've got gates here and gates here so that you don't inadvertently go into them. And then obviously in here, what you've got is you've got reverse pitch on the blades. And what that does is that obviously throws the air forwards instead of backwards. And instead of causing drag, actually positively slows the aircraft down. So in effect, what you end up with is you end up with this bit here, where the fuel computer is involved. And then these two bits here, the lever, all of a sudden also includes the prop and in terms of the angle of the blades, and it also controls the RPM. So this range here is a bit of an oddity. We haven't mentioned it up till now, but we'll see it in the aircraft. But there is where we're at with that. So let's just get rid of some of this and we'll look at the specifics of the Dash 8 Q400. Get rid of that, get rid of that, get rid of that, get rid of that. Get rid of that. Now there is a fuel control or a fuel computer setup in here in the Dash 8, which is something we haven't really mentioned up to this point. I will mention it, but only briefly. So in terms of the throttle settings in our Dash 8, let's have a look at what we've got. This is our range of movement of the throttle. Now you'll see up here rating. The reason it's there is because just beyond it, this bit here is for emergencies. But the rating up here, if you like, is the the normal take-off power. So that would be the normal take-off power that's available. Up here you'd have the max power. But in essence, during normal flight conditions, you'd only go to the normal takeoff power. Obviously, as you get down to the bottom, what you've got here is flight idle. And what that means is basically at this point the engine is doing no work. It's just in kind of almost like a neutral gear, for want of a better way of putting it. Then you have your ground beta, which is your fining off of the blades and causing drag. And actually quite often a lot of turboprops won't go into the next bit. The next bit is your reverse, your actual reverse, where you reverse the angle of pitch of the blades and you actually use it to throw the air forwards again and stop the aircraft. So quite often actually turboprops won't get into this stage. They will just use the aerodynamic braking of the ground beta effect. And this is also used in taxiing to moderate your taxi speed forwards and backwards. Now, not all aircraft have the same layout, but in the Majestic Dash 8, you also have a little bit here, which is a flight beta. And what you will find in the air is if you go into the flight beta range, an alarm will go off to tell you that you're into that range. But basically, your normal power range would be here for your alpha, which is a positive angle of attack on the blades. This is normally where your flight idle is. This bit here, in fact we'll draw it in a slightly different colour. So your normal range of throttle would be from the normal takeoff power, there's your flight idle, and then between the flight idle, just above it, there's a very small range here for flight beta, and then below it you've got the ground beta and the reverse thrust. So that's the throttle in the Dash 8 Q400. What do they do with this one for the power levers, or the condition levers I should say? Really, it's dead simple. Let's just do a little tick there. So what we've got here is we've got the 850 RPM detent. We've got the 900 RPM detent. And we've got the 1020 RPM detent. And in the Dash 8, that would be your that's your takeoff position. This would be your max climb, and this would be your max cruise. And in addition, below that, you've got this position, which is the start feather. So if you imagine fuel is on, but the prop is still feathered. And then below that, in effect, what you've got is the final bit down here, and this is fuel on and off. And we'll go into the actual operation of that in the air, but those are your kind of controls. So if you like, this is your normal flight range. And then down here you've got your various others. Now, one of the other things to be aware of is when you're on the ground, you still have an effect from the governor. And what the governor does, in fact, it doesn't include the start feather. Let's get the rubber. Ooh, Mrs. Fnar Fnar. On the ground, you still have the governor. And what you'll find is that that maintains a minimum RPM of 660. And then when you're in the start feather, if you imagine the blades are in a feather position, so they're still causing massive drag, you'll get approximately 210 to 220 RPM. And obviously you don't want to sit in this position for very long. It's not a great configuration for the engine. But that's the right-hand lever on the dash. Clear as mud. Now let's talk about the PT6. The PT6 is slightly different, but not massively so. The PT6 has very much the same sort of thing on the throttle. So what you will find is that in terms of the throttle, it will have a couple of detents, and within those detents you will have a couple of options. So you've got your max power at the top. You've also got down here, you'll have your flight idle. Then you'll have your beta, which is that range. And then you'll have your reverse, which is that range. So your beta's here, your reverse is here, and then all of this would be your available range for your flight range. So that's pretty much that. And then the other one, the condition lever, one of the things we're going to do here is we're going to split it into two. And this one here, the middle one, let's call it number 1 or lever number 1, that is going to be your RPM. Now, same sort of thing as the constant speed prop. If you go back to the video that I did originally on the constant speed prop, it explains a lot about the RPM. But again, what you end up with is the same sort of thing where you've got your max RPM, your min RPM, and then below that you've got your feather. And then the other lever, this number 2 lever, this one over here, well, the one thing that's missing from here compared to the Dash 8 Q400 is fuel cutoff. However, it's not quite that simple, because in addition, if you remember, we had a number of settings on the right hand lever for the Dash 8, so this has fuel settings as well. So you would have down here, you would have the cutoff, then you have a low idle, and then you have a high idle. Now really all these do is change the RPM, the baseline RPM. So they're not like this RPM, which is your flight RPM, for want of a better way of putting it. These just change your baseline RPM when idling. And as a result of that, really, once you're airborne, these are used very little, because there's, as I say, there's no real fuel metering that you would want to use airborne with this. So really this lever is pretty much a straightforward one. Once your engines are started, you're just going to use that as, if you like, a fuel tap. This one's dead easy. You're just going to use it to set your RPMs, and or if you have to feather an engine, you can use it for feathering. And then likewise the left-hand lever, the fully left-hand lever one. In fact, we will just clarify that. Let's get rid of that. Hello? What's gone on there? We'll just clarify that by getting rid of all of that. And in effect, we're going to point out that that is that. So your left hand lever is your throttle with these ranges, your middle lever is your RPM with these ranges, and your right hand lever is your fuel cutoff. Without further ado, let's jump into the aircraft and see it in action. Welcome to the Dash 8 Q400, which is by Majestic, and it's possibly one of the finest aircraft ever to be created for FSX and P3D. And actually it's a little while old now. It's not exactly the newest aircraft, but it's hung on to the mantle of probably the finest turboprop ever to make it onto the simulated world in FSX and P3D, and I absolutely adore this aircraft. I've not had it for very long. It's a very fun aircraft to fly. It's got I'd say a fairly high level of automation for a turboprop, but nothing compared to say a PMDG 737 or even the Aerosoft Airbus range. It is just a really nice aircraft to fly, and one of the reasons I like turboprops is generally they don't come with all the bells and whistles, so you still need to fly them, and you do indeed need to fly this. So why are we out here? You know, given the fact that all the gauges etc. are on the inside, why are we out here? Well, this picture should tell everything. Being a free power turbine, these are the modern style scimitar shaped blades, absolutely gorgeous, very good for efficiency, very good for the propeller efficiency. However, you will notice that if I were to move, you can see that they are in the feathered position. So if you start turning these, there is a massive amount of drag as these flap against the air, whereas the fixed shaft turbine, you will see these in a fine position, so that they cut through the air once they start turning. Why would you want them to cut through air? Well, it's to reduce drag. So you have your start locks so that you can have these cutting through the air if you were in a fixed shaft. And it allows the fixed shaft to accelerate without too much drag. Of course, in our aircraft here, we're a free power turbine, and our turbine can accelerate on its own and then leave the free power turbine section with the propeller attached to figure itself out. So it doesn't need to start in a fine condition. Obviously it can start in a fine condition, but generally you'll often see them in the feathered condition. The main reason for that is that the feathering is controlled by oil pressure, and if it loses the oil pressure, the blades automatically go into a feathered position. So that's why you quite often see them feathered once they've shut down. You can obviously do it manually, and there are other systems, auto feather for example, that can be used for it, but that's generally why you see them on the feathered stops there. Now the engine layout, we discussed that previously. The engine layout with this thing is what I would consider to be a straight through setup. Actually it's got a bit of a kink because basically the engine and the prop aren't in line. The reason being is you've got a gearbox. You know, the engine turns over at tens of thousands of RPM. This turns over at 2.5 to 4,000 RPM depending on the aircraft. I think the maximum you'd expect out of a Dash 8 is 1020 RPM. So this is turning a lot slower than a gas turbine engine. Don't forget, we've actually got two sets of systems, or two systems in play here. One is the gas generator, which invariably with this layout will be ahead of the free power turbine. So the turbine blade for the free power turbine will be at the back with a big long shaft running through, and then you've got your gearbox here, and in the middle between the prop and gearbox and the free power turbine running around the shaft you would have your gas generator. So intake here, air comes in, gets squish, suck, squeeze, bang, blow. So suck, squeeze, bang, blow, blown out of the free power turbine blades, and away you go. So let's jump inside and without further ado have a look at the gauges and stuff. Here we are, beautiful work of art. Before you get all excited and carried away, I am not going to do the full checklist. That takes time and I really can't be doing with it in a video like this. So we've got the APU on, that's all I'm really going to worry about too much at the moment until we start messing around with switches. As I say, also the chances are we're not going to go through the full process. So let's have a look at the controls. Put the parking brake on. First of all, power levers. Now, in the normal aircraft you would generally, in most aircraft, I don't know specifically about the Dash 8 Q400, but you would have a detent at flight idle, so that when you're flying normally the levers will naturally come back to this sort of position and you won't inherently be able to pull them back into the beta range, the ground beta range I should say. So if you remember when we looked at it, we had rating power at the very top. Actually with a lot of turboprops you can go beyond that into an emergency power setting, generally used if you've lost an engine more than anything else. Gives you a bit of a power boost. However, you've got your max power in effect up here. As you come down, flight idle is obviously the speed where the engines are idling and you're in flight. Just ahead of it though, there's a very narrow band where it's in flight beta mode, and below flight idle, from flight idle down to disk, is where you've got your ground beta. So this is where you're getting drag predominantly. It starts probably about here somewhere in terms of the air alpha's down to that line, which is your positive blade pitch. Then you've got your beta range, which is when you start to get towards in effect producing very little thrust, but what happens is you start to produce drag because you've got big disking props. Below flight idle you've got your ground beta range, and then to disking in effect is a sort of a neutral position, and then below that you've got your reverse thrust. So in terms of the reverse thrust, I haven't got it mapped to a joystick, so I have to press and hold F2, and there we go. Condition levers over on the right. As we said, there's no real metering involved. It's worth pointing out this is a FADEC aircraft, so a lot of the engine parameters are actually controlled by computers. Very clever things. Bit mysterious, some wiggly amps in a box somewhere that control everything. We like that in some respects. In other respects it's a little bit suspicious. We don't know what they've programmed in there. But these levers, fairly simple. They have detents again in the Dash 8 Q400, so they have a number of positions. So you have fuel off, as we said it's not metered, so it's a fuel cut off. In the Dash Q400 we've got this position here, which is a start and feather. So this is where you would start. So this basically means there's fuel on and the engines can start, but it means the props are still in a feathered state. We'll have a look at that in a moment. Once you go to 850, it actually unfeathers the prop there. Minimum 850, then you go 900, then you go 1020, which is the maximum prop RPM in this aircraft. You would use 1020 for takeoff and for landing in preparation for a go-around if you needed to do so. 900 is your max climb and 850 is your max cruise. So it's all fairly straightforward up to this point. This set of buttons up here, worth being aware. I don't want to disconnect the roll system. Clicked, bad clicking. This system up here is quite interesting. It adds another dimension. Not all aircraft have this sort of thing, but basically what it does is it has a certain amount of systems that allow you to override the prop lever. So we said that normally max climb would be at 900. This allows you to override it, so it provides climb power at 850 RPM. Max cruise we've said is normally 850. You can use this button to set it to 900, but you leave the lever in the 850, and basically that allows you to fly a bit faster. So in effect what happens is you'd take off, you'd climb, you'd get to your maximum altitude or your preferred altitude with your lever set to 850, and you want to go a little bit faster, you can press that button without moving the lever. This one is generally used to have a quieter climb. So although you'd move the lever to 900, what then happens is you decide you want a quieter climb, and you press your max climb button here, and it will change the climb parameters of the FADEC system so that your props slow down to 850 RPM even if the lever's in the 900. It can be overridden by either moving the lever or deselecting the button. A couple of others here that are potentially significant, purely to the Dash 8 Q400. Reduced takeoff power, where you can press the buttons to change the torque. Each press, I think, decreases it by 2% from maximum. Reset it, obviously. Max takeoff power. That's basically to get absolute maximum out of the engines. Maximum. What we have here with the rating here is takeoff power, normal takeoff power. If you want the absolute maximum the engines can produce, you can go to max takeoff power. Not generally used because it increases wear and tear on the engine. And then you've got reduced NP landing. Now that's quite an odd one, really. Reduced NP landing. So it's the reduction. NP, N means speed, P means prop, so reduced prop speed for landing. And what it actually means is it allows you to come in with the aircraft with the props working at 850, but you have the levers at 1020. So what then happens is that the props are only spinning at 850 as you come into land, and if you then have to do a go around and you put your power levers all the way forward, the prop automatically goes back up to 1020. That's my understanding of the system. I've never really used this, there's no real need to. A couple of other controls to be aware of. This one here is auto feather, so you can select auto feather on the system. What happens there is there's a comparator between the two engines, and if one engine fails, it can immediately detect that, and then it obviously feathers that engine so that you have minimal drag in the event of an engine failure. And of course there's the flip side that you can also use alternate feathers as well. Now don't forget that actually if you were to pull this lever back to here, start and feather, then you would actually manually feather the engines as well. Clear as mud. Right, let's have a go at this thing in terms of getting it all started and up. As I say, I'm not going to go through the checklist. We have got the APU running with the bleeds open, so let's just get this thing started. Press that. Because it's FADEC, you can actually move this lever up quite quickly. And what you can see here, in fact what we'll do, we'll just quickly pop outside. You can see the blades are turning quite slowly at the moment. They're starting to speed up. But if I pop back in again, what you can see is the fuel flows up here. The ITT is coming up as the fuel's burning. The speed of the high pressure and the low pressure turbines, which are, this is, as I said previously, this is a 3-spool engine, so it's got, in terms of the gas generator, it's got 2 systems, so it's got high pressure and a low pressure. And then you've got your torque, which is an indication of your overall power being used by the engine or produced by the engine, and then your prop RPM. So in effect you've got 3 RPM displays. And these two during a start will come up, that one will come up first, because this is the one that the starter drives. That one will come up second, and the prop in theory should come up third. But really once it's started, the FADEC system in this is very good at controlling all of these things, so you generally won't see too much drag when we're messing around. However, what we can do is we can start engine 2 as well. Should have put position lights on, but as I say, I'm not going through all the checklists, I'm not interested. In fact, they were on. How silly of me. So if we pop outside now, the element that we're looking for, and this is the interesting element now, well I say interesting, it's pertinent. This is our feathered prop, but if you look at the width of the blades here, you can see they're still feathered. They're turning at a decent speed, but they're still feathered. When we go back in, go down here, you can see that they're only turning at 210 RPM. So in effect what's happening is, even though the core engine of the gas generator is running at a decent speed, the prop, because of the drag, is down at 210 RPM. Normally the FADEC system would have an absolute minimum RPM of 660. Obviously when you then advance the power levers in terms of the governed range, it takes it to whatever setting you've chosen here. But fundamentally at the moment it's 210 because the prop's feathered, but you would not normally use it in that set of circumstances. So let's just go down here and we'll just advance the lever up to 850, and then if we pop outside again, you can see that the prop has now gone fine. So the prop is in a much better condition. So in effect what we had was our start position where it's the blades were still feathered. Once we've increased the RPM, the blades have fined off and the engine is in a better position then to operate. And you can hear it running up and accelerating, which is a lovely, absolutely gorgeous feature. There is a feature of this that I will point out. Now, power levers are in the ground beta range at the moment. So let's just move over this way a bit. If you remember, I'll move this one out of the way. We have our normal rating power, we have alpha all the way down to flight beta, just above the flight idle, then we have flight idle, and then we have ground beta. This right hand prop is running in ground beta at the moment, which is why we have the number 2 up here to tell us that engine 2 is running in the ground propeller range, so it's not moved beyond flight idle. If I move it beyond flight idle, so in effect it's going to be fine, 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 as soon as I move it beyond flight idle the light goes out and it tells me it's into the range of power used for flight. If I bring it back to disking it comes back on again. So that's the basis of the controls for the engines. We'll just quickly get number 2 started as well. As I say, I'm not overly concerned about whether it's the correct start procedures in terms of all of the checks. Let's go outside and have a look at what's happening with that. You see, it is turning in a feathered position. One of the things to point out, if you remember, we had quite a good high pressure turbine coming up. You can see the low pressure turbines only just starting to rotate, and the prop is still coming up slowly. So this comes up as the high pressure turbine very quickly, the high pressure spool in the engine. This comes up as well, and the prop starts to come up as well. So these two are in effect being driven by the airflow from the high pressure turbine initially. Then they start to settle out. You can see we've got very little torque at the moment. The other thing to notice, if you remember, I said that once we're into the out of the ground, out of the feather position, it allows the props to spin up to 660. So we're at 660. And if you just look outside, you can see that one prop's feathered, the near one, and then the other one is still nice and fine pitch. So let's just put it back inside. Let's stick this up to here. And in fact, what we'll do, we're going to need to take that off. My mistake, my bad. Let's put that all the way up there, that all the way up there. We'll stick 10 degrees of flaps on. I'm not even going to bother with the arc too. We've got the flight spoilers on. We're still in ground range. Let's just put taxi on for a moment. Put the yaw damper on. And what we will do is we will set the heading so that we can go on to autopilot immediately. We'll set the altitude to somewhere in the region of 6,000, not 10,000. Well, we could go up that high, but it takes a little bit too long for this video. So there we go. That's a very basic setup for the autopilot, ready to go. Now both engines are at 660. The other thing to notice, now that we're into a potential flight range for these levers and we've moved them forwards to 1020, it's now telling us that the levers are in the position for NTOP, normal takeoff power, for which the maximum torque setting, or the torque setting the FADEC will give us, is 90%. And you can see now it's got the little sort of blue, cyan blue carets here, the little triangles telling us that when we advance the power levers for normal takeoff power, that's where we're going to get to. So pressing that, max takeoff power, you can see the annotations change, MTOP 100%. If you don't act on it, it will go back to the NTOP 90%, which is fine. What we're then going to do is we're going to advance the throttles for takeoff in a bit, and you'll see this go up to the 1020 as the governed speed is allowed to increase. And as I say, this is a FADEC system, so there's not really a lot of lag in this system compared to other turboprops. So it's potentially not the best one to use to demonstrate that. However, it is the best one to demonstrate the following. If you remember, we discussed the prospect of disking and control of speed on the ground. If I take the brakes off, we are in disking, and we're right at the bottom range of the disking for the ground. And you can see we're ever so gently creeping backwards. If I use the throttles and advance the throttles a little bit, we're still in the ground beater range, look, because the lights are still on. So we're still in the ground range, but we've stopped, and then if I advance them gently, you can see we're going forwards. So in effect, this is the only aircraft I have come across. Let's just put the props a little bit further forwards, get a little bit more speed. Still in the ground range. I'll bring it back, and you can actually hear it and see it decelerating the aircraft. It's one of the few aircraft I've encountered that does that. And a lot of turboprops in real life won't even go into reverse thrust, they'll just go into disking, because such is the aerodynamic drag of the props in that condition that they can stop very quickly even without going into reverse thrust. Once you go into reverse, these things will stop remarkably quickly. But that's another story for another day. So let's get ourselves into flight. We will, however, pop our strobe lights on if I can remember where they are. Landing lights can go on. We'll stick the heaters on for various things. We can turn the APU off. Let's just get rid of all that. We'll just do it the wrong way and just turn everything off all in one go. Don't need the bus tie on. Everything else is looking good. What warnings have we got? Inboard anti-skid and outboard anti-skid. There we go, so that's all good, all the warnings are out. We've got NTOP 90% set up, and what we'll do actually is I will change the view to here. I shall cause motion sickness as I go, and what we can do then is we can watch what happens in terms of the controls. I'll just move slightly to the left so that I can actually see the runway, and we'll see where we go. So initially advancing the controls, you can see the RPM's not doing a great deal, but you can see that actually the power's coming on as the torque's increasing, and then as the torque increases further, you can see the RPM starts to rise. We're out of beta range, and we can advance the throttles all the way. And you can see now the torque's equalised at 90%, which is what we'd asked for at NTOP. And the prop's overspeeding a little bit, not too much of a problem. I'll just reduce the power levers. I'm watching this, I'm not watching outside, which is why I'm steering all over the place. But the governor's working, the prop is at the speed we wanted, and the torque is at 90%. So let's get ourselves airborne, positive rate, gear up. We are going to climb quite quickly in this thing, so we can probably go all the way to flaps up straight away. And then what we're going to do is we're going to press the following buttons. We're going to press indicated airspeed, alt select, and then the autopilot on. And where's heading gone? There we go, heading select. So heading select, indicated airspeed, alt select, and autopilot's on. Now that we're into our initial climb phase, we can bring the props back to 900. And then what you'll see is the max climb annotation comes on 91%, so the props are coming back to 91% in terms of torque. The prop speed's down to 900, and then what we can do is we can see that the interturbine temperatures slow down. Fuel flow is pretty much what the fuel flow is. So that's where we're at with that. If I want to do a I've never really done this before, so max climb, press that button, and you see it goes to max climb, still 91%, still 900, so let's see what happens if we do this. Let's pull that back to there. I've never really done this. Max climb at 850. So we've still got the same max climb torque setting, look, but we've got a quieter aircraft with the props running at 850. And then we can overrule that and go back to 900 if we want, still on max climb. So really at this point it's more managed by the aircraft than anything else in terms of the FADEC. But what we do is we choose our prop speed based on the phase of flight we want. And really once we get to our levelling altitude, that's the point where we would choose 850. And really that's it. The only thing I've got to add to that is because it doesn't have an auto throttle, so I've got 1,000 to go, because it doesn't have an auto throttle, certainly at low altitudes below 20,000 feet there is a very strong possibility of this thing overspeeding. So it's gone into alt capture, look. So as a result of that you do still need to manage the power levers. There's no auto throttle on this, so as it levels out what we can do is we can bring these back to 850, and there we go. So that's us, and you can see now it's gone to max cruise, 87% torque, and in theory that little caret there means that even without moving the levers out of the power, the rating setup, it's set the engine limit. So I haven't moved the power levers, it's gone 90% for normal takeoff, 91% for max climb, and then down to 87% for max cruise. All of that is through the FADEC. I haven't moved those levers, all I've moved is these levers. However, you can see it's quite a powerful aircraft, so I'm going to have to bring them back because otherwise we're going to exceed VNE, look. Okay, now the other thing to be aware of, and we'll see how the autopilot copes with this, and it's a pretty slippery plane this, to be fair. It's really quite quick. It's renowned actually for having very good sector times on short sectors, being able to compete with the jets. What we're going to do is we're going to bring the #1 engine back to a feather position. You can see the instruments immediately start to change, lose the torque. The RPM comes down to 1300 because the blades are feathered, but we've still got decent ITT because the engine's still running. You've still got the fuel flow, but you can see really the high pressure spool of the engine hasn't really changed much, and the low pressure one has. So this is back to our sort of idling speed and our idling situation. The only difference, if you remember, when we were in this position on the ground, we had 220 RPM. So in effect what's happening is we've got increased drag on the blades. Now this is a bad situation in an aircraft, is to have an unfeathered prop. We'll just go outside, have a look at what it looks like. You can see it spinning, and now what's happening is it's basically spinning slowly but creating a massive amount of drag because it's not quite feathered. Or it shouldn't be quite feathered. In fact, no, it should be. What am I talking about? But it's into an approximately feathered position, but the engine's still running. So what we would then do in real life, we'd recognise that and we'd shut it off fully. And then you start to lose some of your services, and you can see that the aircraft is now still controlling us. This is why I'm on autopilot, is because I can then yes, 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 we know there's lots happening. but you can see now the engine is pretty much completely shut down. I would anticipate when we look out the window it's still going to be turning of some form just because of the wind and the windmilling it, but really that's all there is to the props on this. If you're going to go back to a takeoff configuration, obviously what we're going to do pop that on, pop that back up to start feather, and the engine will start to fire up again, which would be nice. Be nice to have the engine running again, make two of them. Now the only thing to be aware of now is that if you then have to go back into a climb, you have to move your climb lever, your levers back into the climb situation for max climb at 900 RPM, and then likewise if you're coming into land you move them back to 1020. But really with the Dash 8 Q400, the only thing really to be mindful of is this little panel down here in terms of setting your max climb and max cruise. So really guys, that's about the most of it for this thing. That's how the levers work. That's in relation to the turboprop setup. What I would say is if there's any real life Dash 8 Q400 pilots out there, I would ask that you have a look at the comments section and add your thoughts, purely out the fact that you guys have got the type rating, I haven't. So on that basis, that's the props. You can see it's coming back up from its 210, it's coming all the way back up into the governed range of the prop again, up to 850, which is our max cruise. And again, we've got the right annotations here for it, and the engine stats are all back. That's that, guys. Let's go and jump into the Beech 1900 then. Hi guys, and this bad boy you're looking at is the Beech 1900D, and it's in X-Plane 10. Oh yes indeed it is in X-Plane 10, and this is freeware scenery, by the way. All of this is default. I've got the tree line scenery in, which is a freeware, which sometimes has very odd things, sometimes not, and this is freeware Birmingham scenery, which is nice because it's actually got the runway extension here for runway 15. Not bad for something that's free, although I've yet to hear their mating call, but the Monarch Airbus do seem to be mating over here. Some sort of ritual, I'm not quite sure what. But, yeah, really rather dubious. But there we go. Right. In terms of the aircraft, well, the Carenado Beech 1900D is not a study sim. The only two turboprop study sims I've come across thus far, and there may be some others out there, but it's the Dash 8 Q400 from Majestic and the Jetstream 4100 from PMDG. Pretty much everything else is not a study sim in terms of turboprops. The only things I haven't tried is I haven't tried the Turbo Duke in terms of the FSX P3D Turbo Duke, and I also haven't tried the Duke in X-Plane 10, or indeed many of the turboprops. But this one will do for what we're after. So, what are we going to look at to start with? Well, the first thing is the engines. In true turboprop style, for the free power turbine, you can see the blades are feathered for the start position, and they are exactly as one would expect. However, here's the interesting bit. In here, in this dark blue bit here, is the PT6. Okay, the PT6. If you remember back to the bit where we talked about the engine configurations, this is the one where the air does 280-degree turns. So this is the air intake. Down here is the intake for the oil cooler. This one up here is the main air intake for the engine. And the air comes in, and it comes down here, and it does a 180-degree turn. And it goes into the the compression. The compressor section of the engine. So with a straight through, we would expect the compressor, then there's a shaft, then use your turbine blades to drive the compressor, and then you've got, in the middle of all of that, you've got a shaft that runs all the way through to the free power turbine at the back. Different now. Air goes in, air turns 180 degrees, air goes through the compressor, keeps going forwards now in the engine bay, goes through the turbine blades that turn the compressor, then keeps going forwards. By now, it's had hot air and fuel and been ignited, got a lot of energy in this air, and it's got to go somewhere, so it drives itself through the free power turbine blades, which would be somewhere about here, three power turbine blades obviously connected to a shaft to the actual prop, and then the hot exhaust gases with most of its energy expired or expended comes out the exhaust here. So in effect you've got like a sort of U-shaped gas flow. It comes in, goes round, and then almost an S shape actually, then it comes out the exhaust. And that's the PT6 layout, which is why it's subtly different. In effect, it's got this bit here will have the free power turbine, and this bit here will have the actual gas generator section. So without further ado, let's jump inside. I will not be doing the full and proper and frank checklist. Two reasons: A, we don't need it for this, and then the second reason is that I haven't flown this in a while, so I'll just get it up and running and we'll get airborne and look at it that way. I don't want to waste too much time. So let's have a look at the control levers. Let's get down. Right. Dash 8 Q400 had 4 levers, and basically the two on the right, the condition levers, were a combination of these two. If you remember, you had a feather position at the back, you had a ground idle and a flight, a ground running position and a flight running position for them, and you had your 3 sort of detents for your flights. You had your 850, your 900, your 1200. You will notice that for the prop now we've got separate prop levers here and we've got separate condition levers. The condition levers now are completely separate, and what they do is they have a fuel cut-off, they have a ground idle, and then above that they have the high idle, which is what they'll fly in, and literally that's it. That's all there is. You know, there's not a lot more to it really. Lever, up, down, done. So you've got a ground idle position, a low idle I should say, which is pretty much the sort of thing you would use if you're taxiing and you don't want to stress the engine. However, for takeoff you would obviously move these fully forward, and that would be you ready for takeoff. So that would be you in your flight configuration ready to go. As I said before, it's not really used for fuel metering. It's just a case of that's what you would run at low idle, fuel cut off, and then all the way forward is in effect your flight idle or your high idle. These levers now are purely for the prop. In terms of they control the RPM first and foremost, so forwards faster, backwards less fast, all the way down to taxi. And then if you were to keep pulling them back, this is your manual feather position. So we'll put them fully forward ready for a start. And then finally you've got your power levers, which are similar. Now unfortunately X-Plane 10 with this model, it can't model or doesn't model the detents. So if I come back to here in the real aircraft, I would then have to lift the levers to go past that detent. So that's your flight idle position, your ground idle position, so full power all the way back to ground idle. Then you would lift them into this range, which is your beta, and then you would go back into reverse. So unfortunately it doesn't model that particularly well. However, that's not a problem for us. We can still work around that. So let's get this thing started and then we can look at the gauges. In terms of the gauges, subtly different because we got that extra gauge which is here. So all the other gauges could or generally are found in a fixed shaft turboprop or a fixed shaft turbine. Interturbine temperature, which is basically how much fuel you're burning and how hot it is. Torque, which is how much torque or force is being transmitted through the shaft that's driving the propeller. Your prop RPM, which is, I mean, that's even as basic as the constant speed unit single piston engine prop. Fuel flow, how much fuel you're throwing in, and then your T's and P's for your oil. So generally speaking, not too problematic. However, this thing, unlike the Dash 8 Q400, does not have FADEC, so it does not monitor any of these dials. And the middle one that we've got to add, or just below the middle, is this turbine percentage RPM, and that's because obviously we've got two systems now. We've got the prop system with the free power turbine and prop, and then we've got the turbine system for the gas generator. So that's what those dials are and what they mean. So we can expect to see changes in these as and when we do what we're going to do with the aircraft. However, we're just going to get this thing started. I don't really care how. So don't need that, don't need that, don't need that. We'll put the AC buses on. We shouldn't put them on yet. We'll put the auto arm ignitions on. We're going to leave, as I say, we can put that on. It's largely irrelevant. I'm just trying to get this thing started as quick as I can. Normalise, single manual stall warning needs to go off, otherwise that gets warnings. All the way over here, we'll put the bleed air on. This is what I'm saying about it not being 100% correct as a study sim would be. But there we go, that's us in a position ready to start. Now I've mapped the starters to 2 switches so that we can watch the instruments as we fire up. So we're going to start the right-hand engine first. You see as I fire up the starters and the igniters, we'll just pop outside actually. Now this bit's correct because the gas generator is not turning fast enough to draw enough air through to turn the prop. It's not because there's any brake on the prop, it's not because of anything fancy, it's just the airflow going through comes under here, if you remember, round here and out the exhaust, but it's not going through the free power turbine enough for us to see any benefits to it. However, what we will do now is we will start the engine and see what happens. Into low idle. So the turbine temperature is coming up, the torque is coming up, it's trying to turn the prop, and you see now the prop RPM is starting to come up. Fuel flow we would have expected, ITT we would have expected because it's lit up, but if you look now the prop RPM is still rising. So let's just have a look outside at what we've got. Yeah, the prop's still coming up to speed. Yes, whatever. Prop's still increasing in speed. It's taking the prop, because of the lag between the turbine and the free power turbine, between the gas generator and the free power turbine, you can see the prop's taking ages to come up. And in a low idle, it should idle at the top of the green really. So we'll let that sort itself out. Pretty much everything else isn't moving and isn't going to move. The torque, as it gets up to speed, the blades will fine off and the torque will come down a bit. So that's that one started. So happy with that. That's all stable. Right, let's just go down here. We'll click a couple of buttons. Your damper can go on. That can all go on. We should have some TV screens coming on soon when I flick that. There we go. Right, let's get the left one started. Same thing. Fire up the starters. And it's starting to spin the core. Not the whole engine as a you know, it doesn't turn the prop and the free power turbine. It's just the core part of the engine, the gas generator. And once it gets up to about 20%, we will introduce the fuel. And then you'll see suddenly the ITT rises. The prop hasn't started spinning yet. However, the torque is starting to rise, and as it does so, now we've got the prop starting to spin. So this is turning it around. You can see the torque on the right-hand engine's almost gone down to nothing because it's not in a driving mode, so to speak, at the moment. So whilst it's doing that, we'll have a look at the behaviour of some of the levers. At this point, the prop RPM is sufficiently low that I wouldn't expect, just the same as the constant speed unit on a piston engine, I wouldn't expect the throttle to have a fat lot of difference here in terms of the prop RPM. It does. Let's have a look at, because we're below the governed speed really, so it is bringing us up to the governed speed. Look, fast idle. So the fast idle governed speed, we're looking at about 1250 there, 1250 RPM. And then once we introduce the throttle, we would expect that to increase. This is stabilised, so now we can bring this idle up. And again, the torque rises as it starts to accelerate the prop, and then as the prop speed settles down, the torque starts to reduce again. And that's us stable with a start. We can turn the ignitions off now. Auto feather can go on. It is on. It's armed. And rudder boost. There we go. So packs need to go on. That's us started. What we're going to do now is we're just going to mess around with the levers on the ground and see what happens. So if we bring the RPM back, you'll see a reduction in the RPM does not take place because we are below the normal governing speed. This is the absolute minimum RPM it will accept. So I'm moving the RPM lever, but it's exactly the same as our piston engine prop. If you remember, we could move the RPM lever, but until the engine is going at such a speed that the governor can kick in, it just remains at this lowest level. So we're happy that that's doing what it should do. However, now if we introduce the throttle, we will see the turbine temperature will go up because we're introducing more fuel. The fuel flow gauge goes up. The turbine speed starts to increase, and as it does, it starts to speed the prop up. It settles at its maximum, which is 1700, and then the torque is settling at 500 foot-pound. And that's barely off idle, look. Just there. Then I can press a button, I can go into reverse. What we'll do is if I increase the throttle with that, you can see it goes into reverse. And likewise the torque increases, which is obvious because we're trying to drive the blades through the air. The prop RPM increases and the turbine increases as well. And basically what's happening is at this point we are asking the engine to go from its idling state. So let's put it back into forwards. We're asking the engine to go from its idling state to increasing its RPM, its gas generator, and also its torque. Well, if you're increasing the torque, it's going to have to increase the gas generator pressure coming out. So there we go. Right, let's get this thing in the air, and we'll go and demonstrate some of the instruments in the air. So what warnings have we got? Auto feather off and rudder boost, is it? I thought we put the rudder boost on. Rudder boost off. I think you'll find the rudder boost's on. Never mind. That's not the purpose of being here. So let's get airborne and see what happens. Okay, now one of the things is we haven't got FADEC, so if you look at the instruments, each one has its little red line. So the ITT is about 800, torque is about what, 3800, 3750 I think it is, prop 1700, and turbine goes all the way up to, actually it goes up to 104%, which always bemused me why you'd have figures like that. The Sea King, for example, the maximum torque you could pull was 111% twin matched, I think it was the phrase, and I was always like, well, why would you choose 111%? Surely the maximum you would design is 100%. Before we go anywhere, we've still got the brakes on. Let's have a look at lag. So what I'm going to do is I'll show you where the throttle is. You'll see it here, right hand throttle, and we'll have a look at what happens. I am anticipating that the gas turbine should accelerate quite quickly along with the fuel flow and the ITT, but the prop will lag behind. The torque, however, will try and drive the prop. So let's put it forward. You see what I'm on about here? The turbine temperature, the fuel flow and the ITT were fairly quick. The torque was fairly quick because all of a sudden we're trying to turn that free power turbine. However, the prop takes ages. And you can see it goes all the way up like that. I'm not going to try and set fire to the engine. The other thing we're going to look at is whether we can overspeed the governor. So let's hammer it all the way forward. And there we go, it overspeeds the governor, and then the governor settles down the constant speed unit. It goes back to its 1700. Close it all off. And again, the prop is the thing with the greatest inertia at this point, so it takes a while to slow down, but you can see the torque responds quite quickly. Now actually a fixed shaft turbine will respond even quicker than that, because there's what we've got at the moment is the delay between this shaft operating and this shaft operating. So you can see this one goes first, then this one, whereas with a fixed shaft obviously these two are linked together in effect, so you don't get the same delay. So let's get airborne. Now, one of the things I've got to do as a pilot is, because there's no FADEC, I've got to make sure that I monitor the T's and P's. Slightly over revved on the torque. You can see it trying to play catch up. Trying not to over torque it at the moment. The torque appears to be the limiting factor. And we should be able to lift off. Now, one of the things I found with this is that I couldn't find a great deal in terms of the instructions for Carenado stuff. I don't think they're particularly great with instructions as far as I can remember. Let's just trim it a little bit to the right and trim it a bit further nose down. Climb at about 160. So I've had to dig out some power settings, and for a 2-engine climb we should be at 3750, which is what we're at, and we should be at 1550 RPM. So it'd be nice and comfortable for the passengers to be down to 1550, at which point just a quick check of the instruments, all in the green. The only thing we're going to do now is bring the prop back to 1550. Of course the prop is this one here, and one of the joys here is we can bring both back together. They've got this lovely little cross thing where you can bring both back together. Still think it's a rudder boost off, but I'm not convinced it is. And that's one of the things I love about this. Look, I go left or right just with the same mouse. I can alter both of them. So that's about 1550, and that would be our climb setting. So 3575 of torque, 3750 torque, foot-pounds of torque. I mean, it's one of the odd things here is that we've got different units. So we've got degrees centigrade, which is metric. Well, yeah, metric. Imperial? Metric, yeah, because Fahrenheit's imperial. We've got an imperial measurement of foot-pound torque. We're back to RPM, which is just a straightforward number really. Turbine is in percentage, and then we're down to fuel pounds per hour. Really odd set of mixing stuff. So we've got metric, imperial, selective number, random percentage, all over the place. So that's our power setting. Now, in effect, it works on the same principle with the constant speed unit as any other aircraft. You know, just a case of being careful with use of the levers. And really, that's about all there is to it. So what we'll do is we'll start to level off now. And levelling off, we should be able to reduce our prop further to 1450. And that would be our 2-engine cruise speed. 1450 and whatever units of torques are required to keep us going at that. So we'll bring the throttle back to about 80%, I think, and then we'll bring the torques back to 1450. That's a nice economical speed to fly along at. Not going to be particularly quick, I wouldn't have thought. If you want to go quicker, then obviously you can choose quicker. But that's the basic premise of how this thing works. And then obviously, if you're going to go in for a landing, what you can do is you can just whack this engine up. Now, what we will do is we will put this onto heading. And what's the heading? Oh, this is one of the things I'm not keen on with this aircraft. So heading. Push to sync, that should be fine. HSI, of course we don't need to worry about. Alt, heading, don't need any of that. Autopilot engage, and it should hold us nicely where we're at. It's quite nice, but it's massive. Look, you can't change the size in any way, shape or form. You can move it around, and it's really nice. It's a lovely autopilot to use, but let's get rid of it. And you can see, according to the book, this should bring us out at about 180 knots. It's a little bit over, so the figures are there or thereabouts. And, you know, really nice to fly. So what we're going to do now is going to have a quick look at what happens in terms of the engine failure. So the engine failure, let's close number 1. All the way back. And then all we're going to do is we're going to bring the prop back to the feather position. So let's bring fuel cut-off. Bring the prop to a feather position, and let's have a look outside and see what we get. There we go, look, nicely into the feathered position. So in terms of the prop here, in effect, get off. In effect, this is your manual feathering position. So if you had an engine failure, let's just pop that back up, stick that back up, and we'll use the starter just to get it going again. Should light up nice and quickly. There we go. And the power's coming back in. Lovely. So that's us all back to where we are. Pretty much we need to get this, not that one, these controls sometimes can be so fiddly. I need to map these to an axis. That's what the problem is. I'm trying to use my mouse. I should be sticking them on an axis. So really that's where we're at. The governor works. You can see when it overspeeds and underspeeds. You can see the inertia that's in the prop. You can see the effect with the torque, the ITT. Everything's consistent. Really, there's no rocket science to this, other than this is not FADEC, so you need to manage this completely yourself. So hopefully that's been of use to you guys. Obviously, if you're going into a landing configuration in this, basically you do exactly the same as a normal constant speed unit. You whack all of those all the way forwards. You hear the props rise in terms of the tone, back up to 1700 RPM. You'll find that the speed will start to increase. Then you can take your autopilot off. Have I mapped that to a button? Nope. That's not mapped to a button yet. So then you can take your autopilot off and you can go and do your landing. I'll leave that with you guys. Hopefully you found it of benefit. What I would say is if there's any guys out there who fly the Dash 8 for real and or PT6 engined planes, please feel free to leave comments in the comments section. You know, obviously it will help us in the sim community massively, and obviously there'll be a certain amount of guarded jealousy from many people in terms of the opportunities that you have on a day-to-day basis. But in the meantime, I hope you enjoyed the video. If you did, please don't forget to tick like, share or even subscribe. It helps me out massively in terms of being aware what you guys want to see and knowing whether or not my content is the good kind of stuff you want to see. And in the meantime, I shall speak to you soon. Take care.